All right, everybody, we're back for Stoichiometry 2.2, and we're going to still look a little bit at isotopes, just a little bit, and then we're going to move into what is called mass spectrometry. Now, the goal of this video is, at the end of it, you should be able to explain and determine the abundance of certain elements, isotopes, based on the information from the sample. Now, also, you need to know the steps of the process, what it goes through to go through mass spectrometry. Now, where do we get this idea from? The first mass spectrometer was built in 1918 by a man named Francis Aston. Now, we talked about J.J. Thomson. This man was a student of his. Now, what was he actually looking at? He started to find out the idea that we have these things called isotopes, which we talked about in the previous video, and how we could actually separate them out. In a mass spectrometer, which is the device that he came up with, particles are turned positive. Sorry, this happens even when I'm doing videos. So, turned into positive ions, accelerated, then deflected by a magnetic field. Now, if this is the case, when this happens, this gives us a different view of, I guess, how things will work. Now, if you remember with the cathode ray tube, we talked about the fact that the curve was sort of elongated because we have the different forms inside the cathode ray tube. This is using a similar type of setup. The particles with large mass to charge ratios are deflected least, are the heavier, or the particles that have low mass to charge ratios deflect the most, are pulled up very closely. This is what I'm talking about. Now, this is the idea of what we use for a mass spectrometer. Nowadays, they're a little bit more sophisticated, but the principle remains the same. We have your ion source traveling through some sort of electric field to knock off electrons, and then it's going to interact with an electric field that's going to cause it to begin to separate. As it separates, we find out, okay, what are the actual amounts of the substance that are there, of the different isotopes that are there, and these are all red on the detector here to the top right of the screen. Now, they have to be ionized so that they can be accelerated and deflected. If there's no charge on them, then there's no way to actually determine or to attract them within the field. Now, how does it work? It's going to go through 4 steps of this process. We've got ionization, acceleration, deflection, and detection. Now, ionization, first we're given, says gaseous atoms are bombarded by electrons from an electron gun, or they are ionized. Now, this is enough energy to make them to give them a +1 charge. Sometimes you'll find that it'll be a little bit more, but most times it'll give at least a +1 charge to work with. Now, step 2, acceleration. We're going to send them through an electric field that's going to alternate back and forth. This is going to help to speed it up. The negative will attract it, the positive will repel it, keeping it moving through. Next, it's going to be deflected. So we have this curve in the overall stream. This is going to be deflected again by a magnetic or electrical field. And last but not least, using electric or photographic methods, it's going to be detected to determine, okay, we had these different things split out, how much of each do we have there? Now, as we said before, heavier ions or isotopes are going to be deflected less, while the lighter ones are going to be deflected more. If you're looking at what we have here, we have neon 20 being the lightest of the isotopes at the top and neon 22 at the bottom. Now, this is going to depend again on the mass to charge ratio. Heavier isotopes follow a larger radius, smaller will be deflected least. Now, if an ion requires a +2 charge, it will be deflected a little bit more. Its mass to charge value is halved. So if we're looking at the values here given to us in the chart, we have 0 to 4, whatever. If we're dealing with neon and it acquires a -2 charge, we're going to end up with half the value of what we had before. So if you notice, we're around 20 here. If it acquired a +2 charge, now we're dealing with values around 10, 11. This sort of gives us an idea of how to sort of work with it. Now, how do we actually read a mass spectrum? If you're looking at the chart given to you here at the top, you notice that we have our our mass charge ratio here at the bottom, and the abundance here. And we found out that we have 3 different forms. and the positions of the peaks are actually going to give us the masses that we're dealing with. Now, the more specific, if we make the scale smaller, we can tell exactly where we are. The height of the peaks, or the peak intensity, is going to tell us the relative abundance. This relative abundance is going to be less than 100. It's always going to be less than 100. So, in this case, we have our neon 20, and it has a relative abundance of 90.92%. It's going to find the majority of the time. Whereas the smaller peaks, and you have to pay attention here, you notice that this is just looks like a little bump. But this is saying that 0.26% of the isotope or of the sample was actually neon 21. So pay attention even for those little bumps in the road. Now, if we're using this information, we can calculate the average atomic mass. This part should be familiar from the previous video. We have our three different versions, three different isotopes with their relative abundance. And so we multiply. This one, we actually just divided the whole thing by 100 once we did it. You can do that way, or you can go ahead and change the percentages into actual decimals. Makes it much easier, but either way you should come out with the same information. Now, the answer that we're going to get after calculating this should be 20.18. Now, when we set this whole thing up, again, it was just to figure out what is the average atomic mass. If you look at the periodic table, you're going to find a value that's very close to this 20.18. Now, what about if you're given, say, the masses, but you're not given the overall, and the atomic mass, average atomic mass, but you're not given the relative abundance? How can we figure that out? We're actually going to use a slightly different formula. Now, assume, given the example we have here, potassium 39 and potassium 41 are our isotopes. We're going to have N, or X, whichever one you want to use, is going to be the number of nuclei. So if I have a mass of 39, since I have 39 as my first mass number, I have N times 39 plus 100 minus N. Now, why 100 minus N? Because if I only have 2, that means that whatever percentage I have has to be subtracted from 100%. So, for the second part, my value gets a little bit longer, and I have 100 minus N times the 41, which is my mass number. Dividing that all by 100 will give me what my N value is, and then from there I can determine my actual relative abundance. So, after we did all of this, we come out with 3,910 as our value, equals 39N, since 39 times N, plus 4,100 minus 41N, because we'd have to distribute this 41 among these two. Once we've done this, we can determine our actual value of N by rearranging the formula. This is going to give us N equals 95. If that is the case, we can then determine that, okay, potassium 39 is actually going to be present 95% of the time, whereas potassium 41 only 5% of the time. This also gives you an idea of why we have a mass number, an atomic mass of about 39.1 AMUs when we deal with specifically potassium on our periodic table. Now, this is where we're going to end it for now. But you want to make sure you take note of these little things, rewind, and we're going to do some more practice with this when you come in tomorrow. Have a great evening, and I look forward to seeing you then.